Once we understand what the core families of functions look like, we can then transform them and get new functions that have similar properties but are moved, vertically shifted, horizontally scaled, all those kinds of options. Fortunately, the mathematical notation is relatively straightforward. Let's review that by looking at the simple function y equals x squared. And we're going to graph that x against y, traditional way. And y equals x squared is the standard parabola that opens upwards, goes through the origin, goes through the point 1, 1, goes through the point 2, 4, 2 squared is 4, and so on. Now, on the same axes, we're going to sketch the graph of y equals 4 minus a half x plus 1 squared. Now you can get that graph by plugging in x values, making a table of values, but the goal of this unit is to have you remember the rules that you learned for transformations and be able to sketch this graph based on a transformation sequence of the graph of y equals x squared. Specifically, if we have a plus 4, that means we took all our y values and added 4 to them. That's a vertical shift up by 4. This minus a half multiplying the x squared is going to be a vertical scaling. And because of the negative sign, it's also going to have a vertical flip involved. And last but not least, this plus 1 is going to result in a shift horizontally because it's inside the function, and it's going to be a shift left by 1. I put this one in a different color because that's often the one that causes the most concern. We'll come back to that in a moment. For now, let's sketch this graph. We have the parabola. We're going to shift it left by 1. So our axis would be here. Then we're going to move it up by 4. So it'll be up to here. And we're going to scale it and flip it. So it'll be opening down now, and it will take twice as long to get to the same y value. Before we would go by 1, now we're going to go by half. On the next interval, we're going to go by 2, down to here. And after that, we would go by 9, which should be down by 4.5. And we're going to get this kind of shape here. This would be the graph of y equals 4 minus 1/2 x plus 1 squared. Now, a frequent student question is, why does a plus 1 in the formula move things to the left, which is towards negative values of x, rather than towards the right, which is our natural intuition, especially given that's basically the way things work in the vertical direction? There are a number of ways to explain that. The way I think of it as, if we look at the x values that it took to get up to, say, 4, we had to get up to x equals 2 before we got to y equals 4 in the original graph. If we add 1 inside this function, then we don't need as much x. We can go out just to x equals 1, and then we'll have 1 plus 1 squared and achieve the same y value. So that means we don't have to go as far in the x, which means everything's effectively translated left from where it occurred before. If you are ever in doubt, one way to check this for sure is to go back to a table of values just for the points that might be considered. For example, we know that this parabola was shifted up by 4, so we know there's going to be a vertex somewhere. We know it's going to be shifted by 1, and if you're in doubt about which way it's shifted, let's take a look at the two values we get at x equals 1 and negative 1 and see what the y values are. This also helps to explain why we get the vertex at negative 1 in this case. When we plug in x equals negative 1, we're going to have 4 minus a half times negative 1 plus 1 squared. And here you see that I need a smaller x to get that value because this all makes a 0, and we end up with exactly 4, and that was our vertex from before. Meanwhile, we're not going to be at the vertex then at x equals positive 1 because we will have had two values, 1 plus another 1 inside this bracket. That'll be 4 minus a half of 4, and that will be 2. And that's in fact what we have in our graph here. That's certainly not where the vertex got moved to. So that points to the x plus 1 structure inside the function leading to a left shift, despite what your intuition might initially make you believe. As a quick recap, we'll just review the types of transformations we see. If we start with a function and we want to shift it vertically, we simply add some number to the outside. For example, if we have x squared and we replace that with x squared plus 6, that would go up by 6 units. Vertical scaling has the same properties as the vertical shift. It's a transformation that's outside the function itself. And we can just multiply the entire function by a value. That's going to take all our values and scale them by that a value. And again, it can include a flip if this value is negative, a vertical flip. We've seen this one. Let's do a different example for this graph. If we had sine of x, again, we're going to spend more time on sine later, but for now, if we took sine of x and replaced it with 3 sine of x, what would that do to the graph? Well, the sine graph would look like this, and the sine graph naturally has peaks at 1 and valleys at -1. That would be the graph of sine unchanged. If we take the 3 sine x, we're going to have exactly the same shape except vertically scaled, stretched out away from the x-axis, so it can be both positive and negative stretching. Or negative values get more negative, positive values become more positive, and we would get a scaled graph like the one shown here. We also have the horizontal shifts, and here the transformation is something that happens inside the function value. So here we could have f of x minus some number or f of x plus some number, and the transformation happens first here. This I find easier to remember by example. If we had sine of x and sine of x plus pi over 4, remember that if we have a plus value here, it is going to be a left shift. So if we had the sine function again, we'll just do one cycle here. The initial peak happens at pi over 2. If we were to shift it left by pi over 4, we would have the same graph just translated horizontally as our graph of sine of x plus pi over 4. If we wanted to shift it right, we would use a negative sign in there. For horizontal scaling, the transformation is putting a value as a multiplier inside beside the x and then applying the function. Now this transformation is also backwards in the sense that when we put a big value in as a vertical scaling factor, the function got bigger. When we put a large value in here, if c is bigger than 1, we actually get horizontal compression, which is perfectly legitimate. It's just a little counterintuitive given what happens on the vertical side. Again, you can use the logic of, if I put a 10 in here, I don't need as big an x to have the same effect on my function, so things are going to happen more quickly. That's the intuition that I typically use when trying to reason with horizontal compressions and how they work. If we have a c value that's between 0 and 1, then we're going to get a horizontal expansion or horizontal stretching, making things longer. And if we have c less than 0, both of these same things apply in scale values, but there we're going to get a horizontal flip. And with those 4 transformations, we can accomplish a surprising amount, as we'll see in the next couple of examples.